Alrighty, welcome back to operating systems. So, whoa, that's echoey. All right, so today it's the first lecture where things are going to get truly weird. So you thought they were already slightly complicated. Today, we'll get through it. So just as a quick recap, so to try and draw a picture to tie everything together we have learned so far. So we know that when we run our programs, they become processes. So we have processes. Well, let's just say we have a single process. So anyone remember things that are in a process? So that's a running instance of your program. So what do we need to run any program? A kernel. Some things that would live within a process. Yeah, I heard registers, and of course they'd be virtualized, right? So we have a set of virtual registers. We'd have something like virtual memory. And that would be like holding the heap, stack, and even globals. So those are some things that are in a process. And we know from the kernel lecture that, well, the kernel is the thing that is managing these processes, and it is running in something called kernel mode. So let's have a line here to separate out between user mode and kernel mode. So the kernel is the thing managing the processes, making everything. Somewhere in user mode, you would have your application. So if your application wants to use any functions from the kernel, what is the name of those special functions? System calls, right? So if I want to go over this boundary here and actually use things, these are our system calls. So we have our application here running in user space. And what could happen too is there's libraries in our user space. Again, if last lecture was slightly confusing from problems from libraries, don't worry about it. We just care that there's libraries in user space that have other additional code. So instead of our application doing system calls, well, we might do a plain old function call into the library, and they might do a system call on our behalf. It's generally what everything in this course will actually use. They'll all be functions in the C standard library that do the system calls for us. So other little things is we also briefly talked about file descriptors. So in the kernel, you can imagine that it's managing like a bunch of different files, file 1, file 2, something like that. So somehow it's managing a whole bunch of files on our machine that may exist on our hard drive. And other things in processes are our file descriptors. File descript. And file descriptors, basically, they're just like an array of numbers. You can think of it as an array of pointers to files. They'll be independent for a process. And basically, each of these numbers just points to some type of file that the kernel is managing. So something like that. And that's all managed by the kernel. We don't know how the kernel represents files or anything like that, but you can imagine that it knows what files are. And the only thing to know about file descriptors is essentially it's an index into an array of file pointers. It knows what files it is pointing to. So I think that recaps everything we've learned up to this point. Any questions about the recap before things get strange? So things are going to get slightly strange today because, well, we don't actually know how to make processes yet. So at the end of this lecture, we will know how to make processes, and it will complicate your life very, very much. But we will get through it. So here's, just so it's in the slide, everything that we thought was in a process. We expanded it a bit to have the open file descriptors, like any files that our process is using. And as we saw as I drew out, it is all managed by the kernel, and that's our application running. So typically, The data structure the kernel uses to keep track of processes are something called a process control block, or PCB. Specifically in Linux, since Linux is open source, you can actually look at this data structure and see all the information the kernel knows about a process. So if you want to browse the Linux kernel code, you can. Again, all open source, but some things it contains, like the process state, which we will get into in a little bit, the current state of the CPU registers, so that's like its copy of virtual registers, scheduling information, which just means like, hey, maybe how long has this run on a CPU for, when should it run next, memory management, so taking care of its virtual memory, I/O status, so any open files it has, things like that, or any other type of accounting information we need. And each process gets a unique process ID, so we'll see this term throughout this whole course. They shorten it to PID, so it just stands for process ID, and that is how to uniquely identify a process. So whenever a process starts, it gets assigned a process ID that is consistent throughout its entire life. So this is a state diagram of all of the states our process could be in. So whenever we launch a program, it is in this created state, so that's why this arrow starts from nothing. So somehow, which we'll get into today, we will create a process, then it is in this created state where the operating system has to like load that file into memory and set it up so that it could actually start executing. After it's done setup, it transitions to this waiting state. And this waiting state you could also name ready. It means it's ready to execute, but the operating system has decided not to actually execute it on a CPU core yet. It's just able to execute. Then whenever your operating system decides that, hey, this process should actually run, it should execute some instructions, it transitions to this running state. So it's actually running, your program's doing something, it's executing instructions. If your program takes a very long time, it may transition it back to waiting state. So it might be like, okay, especially if there's like hundreds of processes running on your machine, it might say, okay, you've ran for long enough. I'm going to put you back in that waiting state or ready state. You're not going to execute anymore. I'm essentially going to time you out, give you a little break, and then come back to you later. So if eventually we decide to start running again, another state we could take is to this block state. And blocked basically means that process is doing some system call, but it's waiting on the disk or waiting on a file or waiting on a very slow operation. So blocked is you do a system call, your process is in this block state, so it can't resume execution because the kernel is doing a system call for it. You can't just keep running random other code. So it'll be in this block state until the kernel is done with the system call. And whenever it's done, it will put it back in this waiting state so that it can go ahead and run again. And then you can see the outcome of doing that system call. And then eventually, whenever you're running, you might make that exit system call, and then you'll go in that terminated state. That's the end of the life of your process. Your process is now done. It's done all the useful work it's going to do. So any questions about that little state diagram? All right, so keep this in our head. Some of it less important. It'll come out throughout this course, and we'll revisit this throughout the course. So we can actually get some information from the kernel about the processes using a proc file system. So this is basically what you're doing for Lab 1. Oh yeah, by the way, Lab 1 was released this morning. Lab 1 is basically, you know, when you have Task Manager, you're seeing all the processes running on your machine, even if you didn't know they were processes before. You're basically writing a version of that, but specifically for Linux. So how it works is there's a standard proc directory, at least on Linux, for different kernels. It's of course different, so this only works on kernel or on Linux. So they aren't real files, they just look like it, but every directory has a number, so that's the process ID, and it represents a process. And in Lab 1, you'll just be going through that directory and then reading a file called status that contains its state, and that's what you'll use for Lab 1. So if I go to the virtual machine, if I like ls proc, I can see here that there's a bunch of stuff in this folder. Can you scroll, please? And then one thing there's a bunch of folders with numbers. Each of those represents a process. So if I wanted to look at a file, let's say 1, and look at its state file, I can get information about process ID 1 that is currently running on my system. Whoops, sorry, it's called status. So it's called status. So I can get some information about it. In lab 1, you'll just be showing the process ID, which in this case would be 1, and then like the name of the program. So this one is called systemd, some number we don't know, and then the state that we talked about earlier, you'll see sleeping. So sleeping is basically that ready state. So Linux has slightly different names than the general ones, but there's all sorts of information about process here. A whole bunch of these we can't read yet, but some of them we can guess. Anything that starts with VM, that's short for virtual memory, so it's telling us a bunch of information about virtual memory and things like that. But that's basically what you'll be doing for lab 1. So you'll be running a process viewer. So how do we actually create a process? So what you might think is like, well, a process is running a program, so maybe I just create one from scratch. There's some sort of magical system call that I say, hey, run this program, and it'll create a process for me. So we could do that. What that system call would do is like load that program into memory, create the process control block, and put in that ready state so it's able to execute. And that's exactly what Windows does. So Windows has a system call called create process or something similar. Turns out Linux and other Unix systems like Mac OS does not have something like that. It actually decomposes process creation into some more flexible abstractions, which is a bit harder to understand to begin with. So what they do is, instead of creating a process like from scratch, they decide that, hey, we're just going to clone the already running process. So what this does is we pause the current running process, copy its process control block into a new one, which reuses all of the information from the process, including variables, including a new copy of virtual memory, copies everything, and then the only way to distinguish between whoever created the process and the new process is just due to a parent-child relationship. So they take this metaphor like fairly literally. So whoever created the process is called the parent, and the newly created process is called a child, and they form a graph. So a parent creates a child, so they're related somehow, and we can take this metaphor as long as you want. So you could have processes that are grandchildren and things like that. But there's a strict parent-child relationship between, all processes on your machine. And as soon as you have two processes that are otherwise exactly the same, they could execute different parts of the program together at the same time, but they have different virtual memory, so they're going to be independent of each other. And this we'll have examples to try and make this clear, because it will probably hurt your brain a little bit to think about. So what their idea is that if you want to create a new process, then one of the newly created child process, instead of doing what the parent was going to do, whatever calculation it was doing, it could just load a new program and turn itself and start executing a different program if you wanted to run something else. So we'll see that at the end of the lecture. So this is the system call we use to create a new process. It is called fork because it's like a fork in the road. We're diverging a bit between the two processes. So this creates a new process that is a copy of the current one. So it takes no arguments, so it's just fork, no arguments, and it returns an integer. And the return value of this fork function is going to be different between the two processes, and that's going to be the only difference between the two processes. So it has the following return values. It returns -1 if it failed, in which case we did not create a new child, and something really bad is happening on our machine if we can't create a new process. and then it will return 0 in the child process, and then in the parent process, whoever did the original fork call, it will return a number greater than 0, and that number represents the process ID of the newly created process. So after the fork, assuming the system call does not fail, there's two processes running. They can access the same variables, but they are otherwise completely independent. So if one changes some variable, it won't affect the other. Like when we saw we had two of the same program running at the same time. Same idea here. It's just happening at a different point of the program. Instead of just starting it, it's like halfway done and then creates a new one. So you might think this is also slow, but the operating system does something called copy on write to maximize sharing. It makes this really, really fast, and we'll get into how that works again as we get through the course. But first, let's just figure out how to use it. So on POSIX systems, you can find documentation using MAN, so it's short for manual. So today we'll be using the following APIs: fork, execve, which is how we start running another program, and then wait, which will be the next lecture. So you can use man function to look up documentation. If it's the wrong one, you can do man number and then function. So if you want to look at system calls, it'd be like man to fork or something like that. So let's just dive into the example. So here is our program. So start off with main. Everyone knows how this works. Execution starts at main, but now the first thing we do is fork. So we do a fork and we get a value returned. Assuming everything goes right, it will kind of appear that it returns twice, but it only returns once for each process. So in one process, this return PID will return a number greater than 0. So it would go into this branch and then print all of this information, sleep for a little bit, and then any of the other else if branches would not hit. It would just hit return 0, and then that program is done. And then the other process, whenever it returns from fork, would return a 0. So that's the newly created process. So it would check this if statement. The return PID is 0. So it's not greater than 0. So it would fall through to this check. And then in this check, it is equal to 0, so it should print off child return PID. And then we can also use a few different system calls. So there's a system call to ask the kernel, what is my current process ID? So I can ask for my current process ID. And then there's this get PPID, which sounds vaguely inappropriate, but that's short for parent's process ID. Not anything else. Get your mind out of the gutter. So let's go ahead and run this. So if we run this, looking at it without knowing processes, like without knowing it's creating a different process, we'll either go into one of the branches, we'll just see 3 lines and that's it. But whenever we run it, we see something like this because there's now 2 processes. So your world is still the same. Each individual process executing this program is still going line by line, but now we have 2 processes. So after the fork, we have 2 processes. One is printing the 3 lines in the parent, exiting. The other is printing the 3 lines in the child and then exiting. And we can see that all these numbers jive, they kind of make sense. So in the parent, it returned process ID, what was that? 4,701. So in the parent, it should have, from fork, the return PID should match the child's process ID. So it actually does match this number. The child's process ID is 4,701, and it got a 0 return from fork. So these numbers seem to make sense. The parent's process ID was just 4,700, and that makes sense because the child's parent process ID is 4,700. So it is indeed this child's parent. So do we have any questions about that? Yeah?
So in this case, the parent log was printed before the child. Is this by luck? Could
Yeah, so that's a good question. So the question is, well, because we have two processes running, am I basically guaranteed that the parent prints its 3 lines and then the child prints its 3 lines? And the answer to that, which makes our lives complicated, is no. So within the parent, we'll always see the parent's 3 lines in order. It's not going to skip. And in the child, we'll see its 3 lines in order. It's not going to skip. But between the two, we have no idea what's going to come first. So it could go child 1, parent 1, child 2, parent 2, child 3, or any combination of that, as long as in one of the processes it's consistent. So we can run that a few times and see if we get any difference. We're basically, whoops, that was different. So we're basically down to luck. And we can see this time when I ran it, I saw parent first, then child, then parent, then child, then parent, then child. Wow, it's almost like I knew that was going to happen. That is actually complete luck. Yeah.
What's the parent's parent?
Oh, that's a good question. What's the parent's parent? So, is there any way I could figure out what the parent's parent is?
PID1.
Not PID1. So the parent's parent is what? This process here. Yeah, through the proc file system. So yeah, let's be curious. So we can actually figure it out. So it is number 3291, and we can look at the status, and it is bash. Oh, hey, that kind of makes sense, doesn't it? Because bash is the shell that I'm typing this command into. So it makes sense that what I typed the command into created this process to run it. Kind of makes sense, right? Everything's kind of connected. So now I know from just doing that, I type this on the terminal, and if the only way to create a new process is forking, and bash is my parent, then that means in bash, in order to create me, at some point it forked itself. Wow, that sounds bad. So it forked itself, and then it somehow ran my program instead. So my program was originally bash, and then it executed my program. Yeah?
So when we call the fork function, so if it's a parent, it always gives the certain number that we are getting, like which is exactly the get PUID, what we get from get PUID.
So when fork returns in the parent, you get the process ID of the child that just got created. Yeah?
Did I understand correctly that fork ran twice here? Or did you call fork twice?
Nope, fork only runs once.
So which branch did it enter in the if and else statement?
So here, so let's try and use the numbers. So here, oh, whoops, that's not the right one. All right, so I have something that looks like this, right? So we always start arguing about our program assuming we're already a process, right? So someone created me. We know now that it was kind of bash. So I like to write in the margin to keep track of which process is where, just in the column. So originally, when we're running main, we just assume we have one process running it, right? And then this process, let's call it 4000, executes fork. It'll be doing a system call, and then magically at the end of it, we will have 2 processes, right? So let's say the newly created process is something, let's call it 4001. So it gets created. It's an exact clone of this one, whatever it called the fork. So they look exactly the same at this point. And now the only difference is going to be the return value of fork. So in the parent, fork returns 4001, and then in the child, it returns 0, right? And now we don't know which one will execute, but after this point, they're going to be completely independent. They won't affect one another. So usually what happens is the parent executed first. So it would create this variable return.pid and then assign it equal to 4001. And then it would maybe check this if statement. This is true. It would print the 3 lines. And let's say it kept going on. It would fall out and then finish the program, right? And then the other process, whenever it decides to run, it would check the if statement. This one's false, right, because it got 0. And then go in here, print the 3 child lines, and then ends. Yeah?
So when a fork returns 0, that means already a child process exists within the system.
No, so when fork returns 0, that means you are the newly created process. So you are the child. And that's the only way to tell the difference between them. Yeah?
I don't know how to word it correctly, but what is this used for? For like branching or like?
Yeah, so the question is, what is this used for, or why is this useful? Well, this is the only way to create new processes. That's it. If you want to create a new process, you have no other choice but to fork.
Why can't you run whatever you want to run on your same program? What's like the difference?
What do you mean? So like, if I want to run the same thing in both cases, I could just have it do the same thing, right? If I don't check the return value of fork, then they'll do the same thing. So like here, we'll write a smaller program. So let's say I want them to do the same thing, right? Printf. So if I do that and run it, how many times will I see hello in my terminal? 2, right? So let's make sure that that's true. Build fork example. So yeah, I'd see it 2 times, 1 from each process. Does that kind of answer it? You might be like, why can't I just like create a new process running a different program?
Maybe I don't understand what a process is itself. Like, is it like, yeah.
A process is just a running instance of a program.
Okay.
And that's it, yeah?
Sorry, what exactly does bash do? Is it like loading itself and then like running this? Or like, I don't get that.
Yeah, so the question is, what's bash doing? So basically what bash is doing, we'll see, actually I'll leave that a little bit, because we'll see how to run different programs in a little bit, and we'll see exactly what bash is doing. Yeah.
What is the significance of the return value that we get, the 1 minus 1 0, or exactly the child process ID that we do by creating a fork? Can we just not only just create the process?
So the return value of fork is the only way to tell who the new one is and who the parent is, or if there's an error. There's no other way to tell. You don't have to use it if you don't want to. So if I want 2 processes like this that do the exact same, I don't use the return value of fork, doesn't matter. Yeah?
Can you explain what, or can you re-explain why we're using the use function there?
The what? Oh,
Line 14.
this one?
No, line 14.
Oh, the uSleep function. I have that for reasons don't worry about, we'll come back to it later. Basically, in the next lecture, we'll figure out why I do that, because if I don't, I'll get some weird problems with printing the numbers. But we'll explain that in the next lecture, yeah?
Is forking altering the same thing? Going to the program and tell me something?
Yeah, so the question is forking and multi-threading the same thing? So they're related. So it's the same idea. We don't know what will execute. Skipping ahead a bit, basically threads share virtual memory, and these are completely independent. But the same idea, they're running at the same, they could be running at the same time, but you're like 4 weeks ahead. We'll get to it. Right now they're independent, it's kind of the same idea. All right, well here, let's brainbuster. What about if I do this? How many times do I see hello? 3? Is that 3 or 3, 4? 3, 4, 5? Let's see. 4. Why 4? Yeah.
Because you forked first and then you forked again, so that's why it's 4.
Yeah, so it's 4. So I had the original process running this. I called fork, and now there would be 2 processes that want to do this. and each of them fork, so each of them create one other process, so that would be 2 new processes created, and then by this time, I would have 4 processes. So what happens if I do this? 8, right? What happens if I do, oops. So first time through the loop, how many processes get created? 2, right? Second time, how many? 4, 8, 16, 32, 64, 128, 256. It gets worse and worse. Yeah, that's not a good idea. So I'll save that. I won't run that. Yeah, so I'll run it whenever we want this lecture to end. So fork is just one single process. Yeah. All right. So other quick little demo here, just to show that they're independent. So I could do like int x equals 3, and then fork, and then both of the processes will have their own copy of x, right? So if in this one I do x equals 2, and this branch x equals 5, and then I print off the value of x equals x. So if I run this, even if the order is really weird, where the child process executes first and it updates x to be equal to 5, and then the parent runs and updates x equal to 2, whenever they both print, they both won't print 2, right? Because they have their own copy of virtual memory. If one makes a change to that variable after the fork, it won't affect the other. So let's make sure that they still have virtual memory. So we compile, we run that, and we see no matter how many times we run this, we'll always get one of them print x equals 5, the other prints x equals to 2, and we can see that indeed they are literally exactly the same. So if I print off their memory addresses, they should be the exact same memory address too, right? Because they're exact copies of each other at the time of the fork. So if I go ahead and run that, I can see that indeed I get one line printed from each process, and they have the exact same memory address because, while they're different processes, they have their own virtual memory. Changing the value in one does not affect the other, like what we saw when we had the global variable at the same address. So same idea here. So any questions about that? Yeah?
So when an address is same, is it because it's virtual that you can override it with a...
Yeah. Yeah, yeah. So all of our addresses in all our processes, they're all virtual addresses. Yeah.
This method for creating different processes only applies to Linux, right? If it were...
So this applies to Linux and Mac OS as well.
Oh, okay, okay.
Windows is like the special case where they think they're smarter.
Okay.
But we'll see how to run different programs. But everyone okay with that? Looks a bit weird. At first glance, it looks like the same program is taking both else branches, which does not make any sense. And indeed, that does not make any sense. The reason why it looks like that is because there's 2 processes running. So there's 2 things running. Typically, every year, it breaks some brains because, yeah, it looks like it's doing some things impossible. Don't worry. Programs still behave as you expect them. There are just now multiple processes running maybe at the same time, which makes things hard. So the operating system, you can see its job is hard. It has to juggle a lot of things because right now I'm running like thousands of processes on my machine. So everyone okay-ish with that? We'll be doing a lot of code examples, so we'll be creating much more. Any other processes? Okay, so I'm going to quickly show you the other system call today, which is how to actually run a different program. So that system call is called execve, And that replaces the process with another program. So this process starts executing a different program. The process ID stays the same, but we just start executing a different program, setting it all up from scratch again. So its API is the following. It has 3 arguments, a path name, so that's the full path name of the program to load, which is like what file to load into memory. Then argv, that is an array of strings, and strings are just arrays of characters. These are C strings. They're terminated by, the C strings are terminated by a null byte, and then the array of strings is terminated by a null pointer. And then there's this environment P, same type as argv, but that represents the environment variables. They're kind of like global variables for operating systems. We'll ignore them for now. And this function returns only if there is an error. And if it is successful, it does not return because this process is now executing a different program. So here is that example for that. So let's look at this. And so I have main. I'm going to print f. I'm going to become another process. I set up its arguments. So these are like the command line arguments that it would read from its main whenever it starts. So by convention, the first one is always the name of the program itself. And then that's the only argument we'll give it. Then we just won't give it anything for this environment thing. And then we'll call execve. So let's say we're calling ls. It lives at user bin ls. That is the path for the file. We'll give it the arguments. And then we'll see here that if it returns -1, it will say it failed. And if it's successful, it should be executing ls, and we see the output of actually running ls. And if it worked, this line will never, ever print. So if we run that, we'll see that our first line prints, we're going to become another process, and then we do execve, and then it's like running ls. And then we don't exist anymore. That line at the bottom does not execute. Whew. So any questions about that? That's how to run a different program. Yeah?
I didn't understand the function exactly. What does it exactly do? Does it go to that separate part and run that?
So let's say main is running as process ID 100. So process ID 100 would print this line, create these variables, and then process 100 does this system call. And since the system call can actually find ls, process 100 gets transformed into run ls. So ls gets loaded, and the kernel loads that ls into memory, this process's memory, and then starts executing ls as process 100. Yeah?
That happens on line 10, or does that happen after you return?
On line 10, yeah. So this does not return if it's successful. Yeah.
What are the implications of it not returning?
So the implications of it not returning, like why would it not return?
Yeah, or is it like bad that it doesn't return?
Yeah, so it doesn't return because this process is now running a different program, right? I'm not running this code anymore. I'm running their main. This program is not running anymore. This process is running a different program.
And does that return?
Yeah, and then that would, execute the main and then exit from main, and then that might exit the process. Yeah. So now with this is kind of how bash works. So how bash would work is, let's say int PID equals fork. And then one thing it could do that if I was bash, so if PID is greater than 0, I can just simulate I'm waiting for another command. Let's say I was like typing something different here. Whoops. And then in the child process, so I could put this all in an else, assuming that it works. So then in the child process, That newly created process doesn't do anything. It just becomes ls and starts running ls. So if I run this, oops. So if I run this, I said I'm going to become another process, and then it says, oh, sorry, I'm waiting for another process. Oh, yeah, because I put the line there. Well, whatever. So it says I'm waiting. Wow, my text is small. I'm waiting for another command. So this would be like bash waiting for you to type in something else. And then the new process it creates says I'm going to become another process. So this is basically how bash works. So I would type something like ls. It would read it from the keyboard, and then fork run ls, and then wait for me to type another command. So every time I type a command, it creates a new process, runs that program for me. So that's basically how bash works. So now knowing that, you could basically write your own version of bash if you wanted to. It's slightly more complicated than that, but that's the idea. All right, any other questions? Let's see. That was without a fork. Yeah? So EMVP, they're basically like command line arguments, but they're global. We just won't worry about them for now. So we might get back to them. We don't really use them. Most people don't pay attention to them, but it's how programs use them sometimes. Yeah?
For A or GB, you're passing ls, right? But like the path is already to user being ls, right? So
Oh, yeah, so that's a good question. So it says, like, it seems kind of silly, like I'm giving user bin ls and then telling it it's named ls, like it seems redundant, right? Let's see, so yeah, so it's actually used sometimes, so I'll show you why. So if I type ls help, it'll give me something like that, right? Like usage ls, and then tell me all the command line arguments it takes. So it turns out that, let's say I run it with -- help. So let's say I called it, say I just gave it a random name. So it turns out some programs actually use that, and it doesn't have to correspond to what the file is. So if I compile and run that, if I scroll up, I can see that it used that name, right? So it said, haha, lol. So it actually, it's just another convention. So like the standard file descriptors are a convention. The convention of like the command line arguments is that the first one should be the name of the program. And it doesn't have to match the file name. You can call it whatever you want. It's, yeah, so there, as part of the message, it reads the first command line argument. So has anyone read in their program the first command line argument? It's always the name of the program, right? So that's just by convention. So it corresponds to whatever you type on the terminal, which might not correspond to the actual name of the file. Yeah?
So this will be equivalent to user bin ls space -- help.
Yeah, so that right there is the same as just running ls -- help, and then part of the thing your shell does is figure out where that ls executable is.
So it will be equivalent to me typing that into terminal.
Yeah, so this does the exact same thing as me writing just ls -- help. Yeah, yeah.
If you just wanted to do the regular ls command, you could like just pass an empty.
So what? The question is, could I just do like straight up that?
Yeah.
So yeah, if I run this normally, then yeah, probably I'll be okay because it doesn't actually read that if there's no error. Turns out you would have hacked, like, yeah, you would have exploited the Linux distribution. So there was one very, very special command. Has anyone ever heard of sudo and used sudo before? So that makes your process the root user and runs it as the root user. Well, it turns out sudo had a problem where it actually read the first argument and always assumed it exists. So if you did this and gave it null, it would actually segfault, and then you could use that segfault to execute any code you wanted, and you could actually have full root privileges because they did not expect that to happen. And that normally wouldn't happen, right, if I type on my terminal. But if I use the system call myself, I can do whatever the hell I want, and they didn't think anyone would be insane enough to do something like that. So yeah, they had to fix that. So the more you know, right? So you should, another reason to take this course is it gives you, if you play around with stuff, you could develop exploits because you do stuff no one thought of before, right? So you didn't know that. You just, even in your own program, you probably didn't check that there's at least one argument before using the one argument. So you actually probably had a bug in all your programs because you never checked it either. So it's like, don't throw rocks in a glass house or something like that. All right, any other questions for that? Or any other fun stuff? Yeah?
Like, I still don't understand the first argument. Like, is it, you can pass whatever you want?
The first argument of the argv?
Yes.
Yeah, I can pass whatever I want. It's just by convention, it's the name of the name, like whatever someone typed to run the program.
Why would you want that, like, to pass, like, whatever you want, to, like, as the first argument?
So there's some, especially for some like command line utilities, there's a famous one called BusyBox where it's the same executable that does like, you know, like cp, mv, like those commands. It's actually the same executable. It'll just do something different depending on the name you give it. So if I run it as cp, it'll copy. If I run it as move, it'll move. So that's just what they decided. All right, so let's have some fun. We're winding down, so while one. So let's just print off. So int PID equals fork. Let's just say so let's say get PID and then PID. Oops. All right, so this should effectively end our lecture today. So yeah, like we said before, first time through the loop, true processes, 4, 8, it's exponential. Exponents are bad, especially if they're executing something. So let's see how smart this kernel actually is if my laptop catches on fire or what happens. Oh, seems to fail. So at some point, someone has thought of this and they have thwarted you. So fork is now failing because I probably created way too many processes and they thought I was insane and probably had an error. So instead of creating a new process, it just gives me an error. Turns out that there's a bunch of them running. Let's see. Oh, yeah, so that's what happens. So I have essentially ran out of processes on my machine. So now if I try to launch a terminal in VS Code, it cannot create a process. So it fails and tells me that. And if I try to launch my web browser, let's say I try to launch Firefox, it worked. Oh, it worked because that process is related to VS Code because it's like a child of it. So the Linux kernel was like, no, you're doing something stupid, but hey, you can launch Firefox, that's fine. But yeah, let's see if I can launch another terminal. So I can see on my machine, so at the top there, that's all the cores on my machine. They're all running at 100%. So my computer is not doing that well. It's actually getting kind of warm, but it's not crashing. So this is actually a new thing. Older systems, they'll just continue making process until your computer dies and runs out of memory. Oh yeah, by the way, do not run this on the lab machines because they might, but anyways, that's it. So